In this video, we will learn about extended Euclidean algorithm. This algorithm is very important as it is used in very famous problems like computing modular inverse. More importantly, the techniques that we are going to learn in this particular algorithm is used heavily for recursive DP, various graph algorithms like DFS and all. So the technique is also important. This algorithm is also very important. So let's get started. Let's try to understand what is extended Euclidean algorithm. In a normal Euclidean algorithm, okay, first of all, if you haven't gone through my video of normal Euclidean algorithm, I will put that into the cards. Please watch that first. In a normal Euclidean algorithm, we only calculate GCD of two integers a and b. But in extended version, we compute x and y to satisfy this equation. So in normal Euclidean algorithm, we only compute GCD. But in extended version of Euclidean algorithm, we compute three things. We compute x, we compute y, we also compute GCD of a comma b. So let's start on discussing few known cases first. See, in normal Euclidean algorithm, we heavily rely on a recursive approach. And that recursion ends when b is equal to 0 and a is equal to g. G is the GCD of provided two numbers, that is a and b, right? These are two provided numbers and g is their GCD. Throughout this video, whenever we use g, it's going to be the GCD of a comma b, while a and b are the provided numbers. So the normal Euclidean algorithm ends when b is equal to 0 and a is equal to g. Watch the Euclidean algorithm video first if you don't understand this statement. So in last stage, we do know the values of x and y, right? This is the equation we have. We do know the value of x and y because a is g and b is going to be the 0. So we can say x is going to be 1 and y is going to be 0. So why are we computing the x and y values for the last stage? See, this is the technique that I earlier talked about, right? Let's say you have some kind of problem P1 and you don't know the solution of it. So you go through some kind of step and reduce it to P2. You reduce it to P3. You reduce it to P4. Now let's say for this P4, you do know the solution. So you do know the solution for this P4. Now what you do, you go back and compute the solution for P3. Then you go back, you compute the solution for P2, and then you go back and compute the solution for P1. In lot of recursive approaches, we use this kind of technique. In recursive DP also we use this kind of technique. In DFS also we use this kind of technique. So this is the normal Euclidean algorithm implementation. So this is the original problem we have P1. It gets reduced to this particular problem P2. Then it will get reduced to P3, something like that. And ultimately it will reach to a state where we will have b as 0 and a as g. And for this particular stage, we do know the solution. That's why it was very important to discuss the solution for the last stage. So we do know the solution for the final stage. Let's call it P4. Now we need to compute it back to P3. We need to compute it back to P2. And then finally, we will have the solution for P1. And that's what we are saying here. Starting from x comma y, which is going to be 1 comma 0, we are going backwards in a recursive call to compute the final answer. So let's say we have found the coefficient x1 and y1 for b comma a mod b. Why we are taking b comma a mod b? See, I have written here normal Euclidean algorithm, right? So let's say you have the solution for this. Now the question is, can you find the solution for a comma b? See, the technique that I just told you. At the last stage you have the solution. And you are going to compute the solution for all the previous stages. But to compute that solution, first you need to prove or you need to have a proper formula so that you can compute the solution in backward in a recursive call. So this is the technique that is used to develop the formula. So we assume that x1 and y1 are the solution for b and a mod b. Why? Because this is the stage that comes after this. So this is P1 for us, problem 1, and this is problem 2. We do know the solution for problem 2, as we just said. We are assuming it to be x1 and y1. And now the question is, can I compute the solution for a comma b? Okay, so this is what we have and this is what we need to find. So we have the solution here x1, we have the solution here y1. Now the question is, from this, can I get the value of x and y? If I can get the value of x and y from this particular solution, that means I'm able to get the value of x comma y from this call, and this is P1 for us, this is P2 for us. There will be P3, there will be P4, but ultimately we will have B as 0 and A is equal to G. And for that final last stage, we do know the solution. So for the last stage, we do know the coefficients. So by using those coefficients, we can actually compute the solution backwards, right? That's what our main objective is. So let's try to solve this problem, assuming that this holds true. This is true, and this is what we need to solve. We can write A mod B as A minus, this is the division operation, and we are taking the floor value. So this is ultimately A by B floor value into B. This will give us the remainder, right? And remainder is A mod B. Hopefully this is clear to you. This is very common. So now, this was our previous equation, right? See, I have written this equation right here. So G, that is our GCD, is going to be B into x1, A mod B into y1. Now A mod B, we know, is going to be this. So I'm just replacing that A mod B with this. So now we have something like this here. Now let's take this A into y1 separately here, and then let's club this B into x1 with this B into y1 into A by B. So I have taken A here, I have taken B here. This y1 we have, and with B we have x minus y1 into A divided by B. Now we are going to compare it with the solution that we need to find. So this is the problem statement that we had, and this is the equation that we arrived. So comparing these two, we get to know that x is going to be the y1 and y is going to be this value. That's what I have written here. See, in this entire solution, we know the value of y1, we know the value of x1, and we do know the value of a and b. So we can find x and we can find y. So what we have proved here is that if you know the coefficient x1 and y1 for this particular problem, then you do know the coefficient x comma y for this particular problem as well. And these x comma y are completely based on y1, x1 and the value of a and b. All these values we do know. And now we are able to finalize x and y based on what we know. Okay, let's try to code it. See, so this is the normal Euclidean algorithm code, right? Now we are going to modify it further. Now we have x and y as well. See, we are returning the GCD. So to get the value of x and y, we are passing it as a reference. So if b is equal to 0, we do know the value of x and y. X is going to be 1 and y is going to be 0. And we will return a because a will be GCD, right? If b is not equal to 0, we are taking x1 and y1. We are calling the function GCD. This will return the GCD value as well. Also, this will update x1 and y1. Right? These x1 and y1 are the solution for b and a mod b. And based on our previous proof, if we have y1, if we have x1, and if we have a and b, then we can get x and y. And that's what we are going to do here. We do know x1, we do know y1. It has been computed in this particular call itself. So we are going to compute the value of x and y. X is going to be the y1 as per our solution, and y is going to be the x1 minus y1 into a by b. This is a floor division, commonly referred as something like this in maths. And ultimately we will return the value of d, which is the GCD value. So hopefully this is clear. See, we are not solving any problem in this particular algorithm. The reason for that is the extended Euclidean algorithm is heavily used for computing modular inverse, the technique that we discussed, right? The technique which is very, very important. If you need to find the solution for problem P1 and you can get to a problem whose solution is known to you, then you just need to travel backwards and compute the solution in a recursive call. So this is the technique which is heavily used in DFS, also in various graph problems, also in recursive DP as well. So this is very important technique. So we learn a new technique, also we learn a new algorithm. That's why we did not take any problem, because this algorithm we will be using heavily in modular arithmetic, and this technique we will be using heavily in graph and DP. The key concept to remember here is that how exactly we derive a solution. So first we need to find the problem whose solution is known to us, a base case, right? In this particular problem, base case was when the normal Euclidean algorithm ends. At that time b is 0 and we have a is equal to g. So we can take the values of x and y. So this is the base case for us. Once you know the base case, now you just have to write a formula so that you can utilize that particular solution in a backward recursive call to compute the solution for all the problems P3, P2 and P1. So we assume that we have found the solution for a recursive call. See, this is the recursive call here. To find the solution for a comma b, the recursive call is b comma a mod b, and we are assuming for b comma a mod b we have found the solution, and those solutions are x1 and y1. Now based on these two values, can we represent x and y? Well, we managed to do that. By using this simple replacement, we managed to represent x in terms of y1 and we managed to represent y in terms of x1 and a comma b. All these values are known to us, right? All these values are known to us. We know the y1, we know the x1, we know the value of a and b, and by using those we can compute the value of x and y, and that's what we have written in the code. See, for the base case we know the value b is not equal to 0, then we are not dealing with the base case. Then we need to compute the value of x1 and y1. That computation will be done in a recursive call itself because we are passing by a reference. Now this GCD will return the value of GCD. Also it will update the value of x1 and y1 for b and a mod b. Now based on this particular solution, right, we know how to compute x and we know how to compute y, and that's what we have done here. We are updating x as y1, we are updating y as x1 minus y1 into a divided by b, and we are returning the GCD. For the better understanding, let's take a problem where we have a as 80 and we have b as 55. So they have given us a value, they have given us value of b, they are asking us to compute x, y and g which satisfy this particular equation. So first we call GCD 80, 55. Remember, we check the value of b. The value of b is not equal to 0. So again we call GCD b comma mod a comma b, right? It's GCD b comma a mod b, right? Now a mod b here will be 25. Again the value of b is not equal to 0. Then we'll again call GCD, which is b comma a mod b. 55 mod 25 is going to be 5. Again b is not equal to 0, so we'll again call GCD b comma a mod b. 25 mod 5 is going to be 0. So now we have reached the terminating stage. At this particular stage we do know the value of x and y. So here the value of x is 1, value of y is 0, and it will return value as 5. Remember, when b is equal to 0, we are returning the value of a and we are updating x and y. That's what I have written here. If it's confusing to you, you can write this code down, and when I am explaining the problem, you can just verify a code line by line. That's also fine. Okay, you know the value of x, you know the value of y, and you know the value of GCD. Now let's compute x and y for this. See, what is x? X is going to be y1. So this is y1. That means this. And what is y? It's something like this. So let's write it down. Okay, so x is going to be 0 and y is going to be 1. Why? x1 is this minus y1 is 0 and here we have a divided by b. So y is going to be 1. Now let's compute x and y for this. Again, this will return 5 to this. Okay, let's compute x and y for this. X is going to be y1, right? Y1 is this. So x is going to be 1. Now y is going to be x1. See, y is going to be x1 minus y1 into a by b. So x1 is this, y1 is this. So x1 is 0 minus y1 which is 1 into a by b. Remember, this was a floor division. So here a is 55 and b is 25. So we will get this value as 2. So we will have 0 minus 2 which is 2 minus 2. So y is going to be minus 2. So x is 1 and y is minus 2. At every single stage, if you check, like at this particular stage, right? This condition will always holds true. B into y is equal to g. This holds true at every single stage. Put the values. A is 5 here, g is also 5 and x is 1. So this is valid for this particular case. Use this particular case. Here you have a as 25, but we are multiplying it by 0. So it will be 0. And we have b as 5 and we are multiplying it y. And g we have as 5. So for this condition also it holds true. Similarly for here, we have x as 1. So we are multiplying a by x, which will be 55. Then we have y as a minus 2 into 25. 25 is our b. So this will be 5 again. Right? And GCD is 5. This condition will hold true for all of them. Again, this function call will return 5. This will also update the value of x and y. What is x? It's going to be y1. Here y1 was minus 2, remember. So here x is going to be minus 2. And y is very critical, which is going to be x1 minus y1, which was minus 2 into a divided by b. So x1 is 1 and y1 is minus 2. See, y1 is minus 2. This minus and that minus 2 will become plus 2 into, now a by b. A is 88 and a is 80 and b is 55. The value will be 1. So it will be plus 2 will result in 3. Okay. So let's check this equation for this as well. So we have minus 2 as x into 80 plus we have 55 into the value of y is 3 and it is 5. Right? So this equation is true for each and every stage. I hope you get the idea. Algorithm is very, very important. The technique is also very important. If you don't understand anything, please do comment. I will make more detailed video on this, or we can take a sample problem, and in that sample problem as well, I will explain this in more detail.